mind then, we can also figure out the gravitational attraction at various points away from the surface of the Earth. Now, if you go anywhere around the Earth, even though Earth has things as high as K2 and Everest, and things as low as the Marianas Trench, in comparison to going to the center of the Earth is way smaller and has virtually no effect upon the rate of G. But if you go into a satellite way up high in the skies, like say 600 kilometers, or go dig down inside the Earth 600 kilometers, that will have an effect upon your gravitational attraction. So how do you figure that? Once we can go through all that nonsense we did before, but we can simplify that. We're going to come up with a simpler equation that relates G and R. So we know that G is equal to capital G ME over RE squared. Okay? So that's what we're using, but we don't necessarily have to use the Earth for that. We can use some other thing, and we'll just call it 1. So, but one thing we do know, well, actually we're going to keep it in relation to Earth, so we'll keep that. We're not going to go into it. But what is important right here is this right here is constant. This value is by definition constant, universal gravitational constant, blah, blah, blah. The mass of the Earth is going to be constant unless we run into the sun or some other planet, we obliterate ourselves. At that point, we're not doing physics problems anymore. So, that's constant. So, I'm going to call that K for constant because we like K. So, we're going to say G1 equals K over R1 squared. Okay? It's the Earth most likely, so we're dealing with that since we're not going to be jumping around on Jupiter or any other planet for that matter. So we're going to use this relationship here. So that means G2 is equal to K over R2 squared. Okay? So we're going to set them both equal to K, so K equals G1 R1 squared, K equals G2 R2 squared. Since K and K are equal to each other, thank goodness, transitive property allows us to say G1 R1 squared equals G2 R2 squared. And this is the equation we're going to use. Now, the problem we're using, I could have left E here, but I think it's better to use 1 and 2 because this is going to stay the same. The constant that we use for the radius is 6.38 times 10 to the 6th meters. It's going to change and come over here because we're going to go above the Earth and we're going to go below the Earth. Okay? So, the example I have on the script is what is the value of G 600 kilometers above the surface of the Earth? Well, that's going to change the value of R2. It's going to be R1 plus 600 kilometers more. So G2 at 600 kilometers or 6 times 10 to the 5th meters above Earth. So that means it's going to go that R2 is going to be 6.38 times 10 to the 6th meters plus an additional 6 times 10 to the 5th meters, which is going to give us 6.98 times, I forgot the right, times 10 to the 5th meters. No, 6 meters. It's a 6 there. Look at the wrong number. 6 meters. That's my new R2. We know G1 is 9.8, R1 is 6.38 times 10 to the 6th. And so we'll just go ahead and plug that in. So 9.80 meters per second squared times R1 squared, that's not R1, that's R1 there, times 6.38 times 10 to the 6th meters squared equals G2 times this thing right here, 6.98 times 10 to the 6 meters quantity squared. So we're going to divide by 6.98 times 10 to the 6 squared, and we're going to find that G2 is going to equal to 8.19 meters per second squared. So the farther we get away from the center, the less gravitational attraction, and that is what Newton's law states. Distance apart, more, less pull, distance closer, greater pull. Okay? Second example, next example, we're going to go 6,000 or 600 kilometers inside. Okay, so it's going to be the same thing as we had about here, except now we're going to subtract 6 times 10 to the 5th. And that's going to give us then 5.78 times 10 to the 6th meters inside here. That's going to get squared. And when we do that calculation, we get 11.9 meters per second squared. So it's a dramatic effect. Now, the last thing you want to know, and this is kind of, if you want to find a way to lose weight or gain weight, this is a good way to do it. The last example asks for what is the weight of a 125 kilogram person on the surface of the earth and then the question is what is its weight there, which is easy, 125 kilograms times 9.80 meters per second squared equals 1,230 newtons. Yes, I can do that in my head. Next choice. The next one is at 600 kilometers above. Well, we calculated the FW for that as being 8.19. So FW for this person is 125 kilograms times 8.19 meters per second squared. And we get 1,020 newtons. So we lost not quite 20% of our weight. So lose 20% of your weight, go to space about 500 kilometers. And the next one is at 600 kilometers below the surface of the Earth. And so FW equals 125 kilograms times 11.9 meters per second squared. And when we do that, it goes up to 1490 newtons. And that's like more than 20%. So, that's how we do the G thing. Be right over here, your practice problems. And there are 4 questions for you to deal with. Be sure you show all setups and answers with your labels. Have fun!